Hello students, welcome to our today's class. Today we are on the third and last portion of the chapter Universe, which is Unit 12 of Grade 10 Science and Technology. So in our previous class, we learned many things related to universe. In our first class, we studied about some celestial bodies. We also learned about the effect of gravitational force, its importance, its consequences in this universe. And in our second class, we looked in more depth about the origin of the universe and what is happening currently. And we also learned about the Big Bang theory and other proposed theory about the universe. So, when we studied about universe, one thing was that everything, every matter, every space, everything comes under the term universe. So when we describe universe, it is not just some celestial body, not just some matter, but everything that is here. So we looked at two different definitions as well. According to Merriam-Webster, universe is defined as the whole body of things and phenomena observed or postulated. So it is basically not just the matter or things, but it also includes phenomena as well. Whereas according to NASA, the universe includes all of space and all the matter and energy that space contains. So basically, universe means it includes, it is about everything here, not just some matter but also the space as well. So today we'll not go more depth on the origin of the universe because we already studied that. However, when we were studying about the universe, we came across gravitational force, right, and its consequences. So today we'll be focusing on other three forces as well. So when Big Bang happened, when we studied about Big Bang, we told that Big Bang is exactly not an explosion but the expansion. So at a very minimal time, when our universe started from singularity, which was a very hot and dense point. So at that time, at a very less amount of time, or let's say within a very split of very minimum seconds, universe started to expand exponentially. So when the expansion was the rate of expansion was very greater at that time, that time was called as inflation. But many terms also, it is also termed as Big Bang explosion, but it is not exactly an explosion but an expansion of singularity, which is just a single hot dense point. So when this happened, when Big Bang happened, lots of other steps followed through this Big Bang, which is where we are now. To reach this state, many steps have been crossed. So when we learned about the origin of the universe, we came where in certain timelines atoms started to form. Before atoms, nuclei started to form, and due to the very hot temperature, nucleus could not be formed because of its extremely hot temperature. And slowly, when the universe started to cool down, they were able to form atoms, right? So and gradually the rate of expansion decreased at some point, but the expansion is still happening. However, the velocity of the galaxies however, the expansion rate seems to be decreasing comparatively. So when we came across the timeline of this all, the origin of the universe after the Big Bang, the steps after the Big Bang, we came across four fundamental forces. In our earlier class, we have discussed something about gravitational force, but that is not the only force here. There are mainly four fundamental forces which have very importance in our universe. So these are our four fundamental forces. We will look at each of them one by one. So in this figure, you can see a timeline where you can see time after Big Bang. See here you can see even in the minimum 10 to the power minus 43 seconds, 10 to the power minus 35 seconds, and 10 to the power minus 12 seconds, you can see here the forces they started to separate. Before this time, or let's say after this time, right after the Big Bang, in the minimum seconds, all these four forces were together. They were inseparable. That state was known as grand unification theory. So grand unification theory, it suggested that these four forces are indistinguishable and they cannot be separated. But gradually, here you can see on the upper side, here you can see the scaling of the temperature. See, the temperature has been decreasing with time. So after few moment, you can see firstly all these four forces were together. After few time, first the gravity seems to be differentiated from amongst this group. So gravity separated from these three forces, and then these three forces were yet to be separated. Gradually, when the universe started to cool down, further strong force also separated. And then electromagnetic force and weak force, they were combined together, named as electroweak force. But according to some time, after some time, when the universe was again cooling down, the remaining these two forces, they also separated. So after some time, we could see that these four forces were distinguished and they were differentiated as well, and then they had their own principles, they had their own necessities as well. So in our earlier class, we had studied about gravitational force, right? So here you can see in this diagram, we can see four different forces. There are few out of many functions have been showed here. So when we talked about the strong force, it is responsible for the binding of nucleus. Electromagnetic, it binds the atoms. And weak force, it is responsible for radioactive decay, which we will study in detail afterwards. And gravitational force, it binds the solar system. So now these were just a brief introduction of these forces. Now we will go into the depth of these four forces first. So first, gravitational force. We have studied this in force and motion as well, and in our previous session of this chapter itself as well. So what was gravitational force according to what we studied? Gravitational force is the force of attraction between any two masses in this entire universe, right? So this gravitational force, it is always attractive and it is never repulsive. So there is always attraction between two masses. Although this gravitational force depends upon the mass and also the distance between two masses, it is always attractive but never repulsive. And secondly, it acts on all the objects with mass. It is also called as the universal force. So this is not just for, again I am going to repeat the sentence, it is this gravitational force, it is not just about the celestial bodies, it is about every object which has mass. So it is also known as the universal force. So amongst these four forces, gravitational force is the weakest one. It is the weakest force. Although it is the weakest one, it dominates very large scale structures. So I already mentioned in the second point that it acts on all the objects and it has a very wide range as well. Although it does not have a certain exact distance of its influence, we can say that this force has an infinite range of its influence. The influence is infinite and it affects objects across the universe as well. When we talked about the formation of stars and how moon is orbiting the earth, how other satellites are orbiting around the earth, it all comes under the gravitational force. So it affects even the object across the universe as well. Another one, it follows the inverse square law. So when we studied about gravitational force, with the term gravitational force always comes the universal law of gravitation. So universal law of gravitation basically states that the gravitational force between two masses is directly proportional to the product of the two masses, and it is inversely proportional to the square of the distance between two masses. That is why we say that it follows the inverse square law, meaning further the two masses are, lesser will be their gravitational force between them. It is responsible, it is important for the structuring the shapes of cosmic structures like planets, stars, galaxy, and the entire universe as well. So basically gravitational force is the force of attraction between two masses, in which this gravitational force is directly proportional to the masses, whereas inversely proportional to their distances. So if there is some objects of greater mass, if both the objects are of greater mass, then obviously the force of attraction will be very noticeable, and they are very responsible for many phenomena that is happening in our universe. When we studied about the life cycle of stars, we mentioned that gravity has had a very key role, very vital role in this state as well. So now let's go into our second force. Second one is strong nuclear force. With the term strong nuclear, you already must have guessed that this force is about, this is related to nucleus, right? Even in this diagram you can see electrons are orbiting around this nucleus, whereas the protons and neutrons inside the nucleus, they are held together, and this the main force which due to which this proton and neutrons are held together is strong nuclear force. So this is the strongest of the four fundamental forces. Gravitational force, it is the weakest one, whereas strong nuclear force is the strongest one. As I mentioned just now, it holds protons and neutrons together in the nucleus. So what if there were no strong nuclear forces? What would happen? There will be no formation of atoms, right? Why? Because if there would be no nucleus, due to which there would be no formation of the atom. Since this strong nuclear force helps the protons and neutrons to stay together, bind together, proton atoms are being able to form. So although this is the strongest of the four fundamental forces, it is of very short range force, which acts within just atomic nuclei, which is nearly equal to 10 to the power minus 15 meter. So let's once compare gravitational force and nuclear force. So gravitational force, it is the weakest one, as already mentioned. Strong nuclear force, according to its name, it is the strongest one. And the major difference is gravitational force, the influence, it has infinite range. Its influence is of infinite range throughout the universe, whereas although this force, strong nuclear force, is the strongest one, it has a very short range. Its influence is not over the entire universe, but as just within the atomic nuclei distance, which is nearly equal to 10 to the power minus 15 meter. Okay, so now let's move on to the another one, a very familiar term, electromagnetic force. So we have heard this term in an electricity chapter as well of grade 10, right? We studied about electromagnetic phenomena, its principle and its various causes as well. So basically electromagnetic force is the force which can be found between two different charges. According to this, you can see in this diagram as well, as we know a fact about charges that like charges, they repel, whereas unlike charges, they attract each other. Here you can see two positive charges, they are repelling each other, and two negative charges, they are also repelling each other because they are like charges. But in case of the third point, you can see the positive and negative charges, they are attracted to each other. Okay, so basically electromagnetic force, it is the force which occurs or which is experienced by two charges. And electromagnetic force, comparatively, it is much stronger than gravity, but weaker than the strong nuclear force. Now we cannot compare anything to a strong nuclear force because it is probably the strongest nuclear force, but in this case electromagnetic force, it is relatively stronger than the gravity. And similar to that, its influence is also of infinite range, but it weakens with distance. Now see, it is again similar to gravitational force. In what way? We can see it also has its influence in infinite range. Gravitational force also had its influence on infinite range. And we can see another criteria, that it weakens with distance. So it also follows the similar principle of gravitational force. See, this force, it is directly proportional to the charges and inversely proportional to the square of the distance between these two charges. Meaning, if we increase the distance of the two charges, then electromagnetic force between them also decreases. Whereas, if we decrease the distance between two charges and bring them closer, the electromagnetic force will also increase. Okay, so basically electromagnetic force is the reason that we are able to use electricity and light throughout this whole world. So it is a very important one. And last one among the four forces, let's say, is weak force. So here you can see some phenomenon happening around here. I will explain it at the end of this topic, weak force. First, let's see its influence as well. So according to its name, it is weak in strength. But as I already mentioned, amongst these four forces, the weakest one is the gravitational force. So this weak force is still not the weakest one. It is weaker than strong nuclear force and electromagnetic force, but not than the but it is comparatively stronger than the gravity. It is also a short range force, and it causes a very important phenomena which is known as beta decay, which helps in the stability of the atoms. And another its important part is it is essential for star energy production as well. Okay, so leaving behind others, let's once discuss about this beta decay. Beta decay, it is a type of radiation decay where either protons are transformed into neutrons or neutrons are transformed into protons, which helps the unstable atoms to become stable. And beta decay, why is it important? If there are more unstable atoms in our universe, lots of radiations will be emitted, which would be harmful to living beings as well. So this force has its own importance as well. So here you can see beta decay. They are basically of two types, beta minus decay and beta plus decay. You do not have to undergo through any particular processes here. It is a spontaneous process and it happens itself. So here you can see, here in beta minus decay, what is the output here? Here the neutron is being transformed into protons, where electrons and antineutrinos are emitted. Here you can see the number of protons and neutrons are changed. Earlier there were 6 protons, 8 neutrons, whereas afterwards, after beta minus decay, there were 7 protons and 7 neutrons. So basically this process will maintain the ratio of neutron and proton. Once the proton number is changed, or let's say it is transformed, obviously a new element is formed as seen here. Okay, and next one is beta plus decay. So what happens in beta plus decay? In beta plus decay, proton is being transformed into neutron. Earlier there were 6 protons and 4 neutrons, whereas after beta plus decay there are 5 protons and 5 neutrons. However, in this case, unlike the earlier one, here they have emitted neutrino and positron. Basically they are their antiparticles, electron, positron and neutrino, antineutrino. They are simply antiparticles of each other, and we do not have to study that in much detail. So basically till now we must know that there are 4 fundamental forces, which are gravitational force, strong nuclear force, weak force and electromagnetism force. So among these 4 forces, The strongest one is the strong nuclear force. The weakest one is the gravitational force. And in the earlier time, right after the Big Bang, for some moment they were indistinguishable, where we call that state as grand unification theory. Slowly, when the universe started to cool down, they started to separate from each other. So now, after knowing these all facts, now let's try to solve some questions. Choose the best answer for the following question. Which of the following best explains why gravity, despite being the weakest fundamental force, governs large-scale cosmic structures? Now let's see. It is asking you, although it is the weakest one, why does it have infinite range of influence? Now let's look at the options. Option A, gravity has a repulsive component at short distance. Okay, so the first characteristics of gravitational force when we studied was it is always attractive, not repulsive. So this first option is obviously incorrect one. Second option tells us gravity has an infinite range and acts on all mass and energy. So this seems to be true. Let's see if there are any other best options. Third one, the gravitational force increases the distance. So this force, it does not make any sense, right? Because we were talking that gravitational force is about attraction. So if the gravitational force increases the distance, it means it is a repulsive force, which is incorrect. Let's look at the last option. The strong nuclear force eventually transforms into gravity, which is again not true. So among these four options, obviously option B is the best answer. Gravity has an infinite range and acts on all mass and energy. Let's look at our next question. If the strong nuclear force were slightly weaker, which of the following would most likely happen? Okay, firstly, we said that strong nuclear force, it is very essential for holding protons and neutrons together, right? Okay, so with this information, let's look at the option. Option A, the gravitational force would increase in strength. Option B, the electromagnetic force would no longer function. Option C, atoms would become unstable and no complex elements would exist. And option D, the weak nuclear force would take over, binding protons and neutrons. So amongst these four options, obviously the option C is correct, right? Because if there will be no holding of protons and neutrons together, atoms would obviously become unstable. Okay, so with this, now let's recall again something about Big Bang. So when according to the most acceptable theories, Big Bang was the most acceptable one, right? So according to Big Bang, all this started, whatever is happening now, all this started from a singularity, a very hot and small dense point. So after this, we came to a conclusion that the universe is constantly expanding. There is expansion of universe, and even Hubbles law supported the expansion of the universe, which was proposed during the Big Bang theory. So the expansion of universe, it is still happening, although the velocity seems to be changing than the previously observed values. So what happens later on? One question must be coming in your mind, right? Will this expansion continue forever, or will it slow down, or will it reverse? So our guesses are, will this expansion like keep on happening? Will every celestial bodies go move away from each other? Will it slow down and maybe come to halt, like maybe stop? Or will it reverse, meaning right now every celestial bodies, they are going away from each other. Now after some time, will they come together or what? So let's see some of the predicted future of universe. So before entering there, let's know about some terms here. Firstly, the average density of the universe. So Basically, the average density of the universe refers to the amount of matter and energy, including both visible and dark matter or energy, distributed throughout the observable universe, also measured as mass per unit volume. We know the definition of density already in our earlier classes. It is simply mass per unit volume. So why are we taking the average density here? Because in universe, in some places, there might be more celestial bodies, or there might be more matter which where it might be dense, whereas in some other places the matters might be pretty less, and their density there it might be less denser comparative to the other regions. So we have to calculate everything and come up with the term average density to know about the to compare it with something else. Okay, so here we are talking something else, means we are talking about critical density. We are going to compare average density with critical density. So basically average density of the universe means we are just taking the average density with all the matters which are present in this universe. Whereas in case of critical density is the average density of matter required for the universe to just halt its expansion, but only after an infinite time. Meaning this density is the requirement which can stop the expansion of the universe. Okay, so now let's see, we will compare it, the values will be compared, and we will see what might happen in the future. So we have three guesses. First one, our universe might be an open universe. Secondly, it might be a flat universe. And thirdly, it might be closed universe. Let's look at it one by one. Firstly, open universe. So open universe, with the term open, we know that it is talking that the universe keeps on expanding. Okay, so how does it happen? Let's say here comparatively, here you have seen rho c, right? This rho c means critical density, whereas this rho means the average density of the universe. So let's say here, if the density of the universe is lesser than the critical density, if it does not match the required density, what happens is gradually gravity becomes weak. See, the objects are moving away with certain velocity, but due to the gravity of matters, some force is still pulling those objects towards itself, right? So but gradually, when this universe keeps on expanding, and if the average density also becomes very less than the critical density, the effect of gravity will weaken. The effect of gravity will weaken, but what is not stopping is the velocity. See, the velocity is not being stopped with any obstacles. Although the effect of gravity will eventually become zero, or let's say after infinite time, it might be very weak, which might not affect the further away objects and celestial bodies, the velocity is still there. The velocity is not zero. So that non-zero, with that non-zero value of velocity, the bodies will be going far away from each other, and it will never slow down. It will never come to stop. So it keeps on expanding, which leads that the universe expands forever, leading to the big chill. Slowly, when the universe keeps on expanding, the temperature of the universe will again decrease, and it will become very chill. That is why we also term this open universe as big chill. And you can see, in case of open universe, you can see a saddle shaped universe, which is predicted to happen after infinite amount of time. So our second guess, this is when critical density is this is when average density is lesser than the critical density. Now let's look at another situation. What if the average density of the universe is equal to the critical density? Now let's see. In this case, if they match the density, the gravity will balance the expansion. We cannot say that it will completely stop the expansion of the universe, but it will balance it. Eventually the expansion will slow down, but it will never completely stop. It will become very slow. It will tend to go towards the value of zero, but not exactly zero. So In conclusion, the universe continues expanding forever, but at an ever decreasing rate, at a very minimal rate, approaching zero expansion speed over infinite time. We term this case as flat universe. As you can see, there will be no expansion, no contraction. It will be like it is balancing the expansion with the gravity. So our third case is closed universe. So you can see the proposed illustration as well. So what is the condition here? The average density, if the average density is greater than the critical density, let me recall you, critical density is the required density to stop the expansion of the universe. But if the average density of the universe becomes very higher than the critical density, obviously the expansion is going to stop. This gravity will become very strong enough to overcome the expansion, which might even bring the value of velocity towards zero, meaning the expansion will now slow down. It will stop at after certain point, and due to the effect of gravity, since there is zero velocity, it is not going anywhere. Instead, the expansion is going to reverse, meaning all the celestial bodies are going to come together. So in conclusion, the universe collapses back into a singularity. See, we have heard the term singularity when our universe began, and now we are going to the future and it's again going to singularity. How? When this, if the average density of our universe is very greater than the critical density, then this process is going to reverse and everything is going to come towards each other. They are going to be held together and everything again comes back to singularity, which is known as big crunch. This state of the universe is known as big crunch. So after that, we don't know, maybe again another universe might be formed from that singularity point. So that is just some predictions with these principles. So here is a simple illustration about the open, flat and closed universe, whereas this is the comparison of open and closed universe, how galaxies are moving away and in the future they will keep on going away from each other in case of open universe, but in case of closed universe they are going to come together after infinite time. And this is again the same illustration of these three predicted future of our universe, which is again shown in graph very clearly. In x-axis you can see, you cannot see the exact time, but you can see time since the Big Bang, and in the y-axis you can see radius of the universe. Here you can see, in case of open universe, since the expansion is going to continue forever and ever, the radius keeps on increasing. Whereas in case of flat universe, expansion is happening but at a very decreasing rate. So radius comparatively to the open universe, flat universe has less radius. Whereas in closed universe, see, we started from a singularity point. From here it's expanding, and in future if it follows this, what happens? It again comes back to singularity, known as big crunch. So these are the three predictions which have been predicted about the universe. So now, so far we studied about four fundamental forces and the three possible future of the universe according to certain criteria. So now let's try to solve some questions. Choose the best answer for the following question. Which factor primarily determines the future of the universe? Option A, the temperature of cosmic background radiation. Option B, the amount of dark matter in black holes. Option C, the average density of the universe compared to critical density. And option D, the number of galaxies in the observable universe. Obviously, you have pointed the correct answer, because if you look at the first option, cosmic background radiation, that was not about the future but about the origin of the universe, which kind of supported Big Bang, right? It was the evidence of Big Bang. So amongst its four options, the correct one is obviously option number C, the average density of the universe compared to critical density. So it is determining the future of the universe. And this is another question. Here you can see a graph. Here you can simply identify this curve that we just studied before few minutes. You have to identify these A, B and C, in which cases it is happening, and you also have to explain the reasoning for this predicted futures of our universe. Okay, so we have come to the end of this chapter. So before ending this chapter, I would like to remind you something. Like, we have studied the chapter universe, right? So we are just studying it theoretically, and maybe we are not exploring it enough in our night sky, which is an open book for us to study about celestial bodies as well. So here you can see, this is a event, this is a past event a few months ago, when we heard some news about the alignment of planets and all. So this is of that time, not the exact date. It is of February 4th, where in the sky we could visualize Saturn, Venus, Moon, Uranus, Jupiter, Mars. So when you go and look at the night sky, I would like to request you to look at the bright stars or bright objects and identify them using some free softwares or free apps, so that you can relate all these in your course books as well. So you can use and predict other further night sky charts for other further events as well, and you can relate it with your course syllabus as well. So with that note, I would like to end this class. Study well and keep exploring the sky. We shall again meet in our next class. Thank you.